Oh, hi. Hello.
Hi.
All right, so I guess we can begin.
Uh-huh.
Okay, wonderful. So it's my pleasure to introduce Professor Andrea Walter. So just a little bit of background, Professor Andrea Walter studied business mathematics at the University of Beirut and got her PhD from the Technical University of Dresden in 1999, from where she also received her habilitación in 2008. In 2009, she became professor of mathematics and its applications at Universitat Paderborn. And since October 2019, she has been math professor of mathematical optimization at Humboldt-Universität zu Berlin. Her research interests are in the field of nonlinear optimization, with a focus on adjoint-based optimization and non-smooth optimization, as well as in algorithmic differentiation. She's currently a member of the board of the International Association of Applied Mathematics and Mechanics, and chair of its activity group on computational science and engineering. So it's my pleasure to welcome Professor Walter, who will speak on optimality conditions for non-smooth functions. Thank you.
Thank you very much for the kind introduction, and also thanks very much to the organizers for giving me this opportunities to speak here. It's really a great honor to give this plenary presentation at the annual meeting, despite the fact that we have this weird situation where everybody stays at home with the home office, as you see in my background. Okay, so as said before, I will talk about optimality condition for non-smooth functions, which is one of my main research topics at the moment. And I present here joint work with Andreas Kriwank, who is also from the Humboldt University zu Berlin. The outline of my talk is the following. So I will start with a motivation. So why is non-smooth optimization interesting? And then I will give some basics on smooth and also non-smooth optimization to prepare the ground for our class of functions. So we define, or we look at a special class of non-smooth functions. And for this special class, we can derive optimality conditions with quite different features than compared to the basic or standard non-smooth optimality conditions. Then I will turn to MPECs, so mathematical program with equilibrium constraints. And there's actually a relation between our class of functions and these MPECs. And I will just illustrate these relations briefly. And I will conclude with a summary and an outlook. So let us turn to the motivation. So where does non-smoothness comes from? So as a very simple example, I stated here the smooth constraint situation. So we have a target function, and we have equality constraints and inequality constraints. So usually one would use, for example, a constraint optimizer to solve these problems. However, one may also, if there is a feasible point, reformulate this using the so-called L1 penalty, which you see here. So you have the absolute value, and you have the positive part function here at this point. In this setting, I just use one multiplier. You can also complicate the situation using different multipliers, but this is just to illustrate you that you can reformulate this constraint optimization problem into an unconstrained one, but obviously non-smooth one. So this is one possibility where non-smoothness may arise. Other examples are robust optimization. Here you can think of a minimization of the maximal regret, and this would result then in a min-max problem, and therefore you see immediately non-smoothness. Another possibility would be train timetabling. So for the design of the timetables for trains, this is an optimization problem, or you can formulate this as an optimization problem. And Christoph Helmberg, in his group, he looked at the formulation that is based on piecewise linear optimization. And again, you see here in this piecewise linear, the non-smoothness. Also, piecewise linear comes into play if you generate local, or may come into play if you generate local models. So for example, this is a work from an energy-oriented research research initiative in Germany, and they use piecewise linear models for their flow problems to approximate the gas flow in a gas network. And finally, since it's everywhere around, I have to mention it here, machine learning. Due to the non-smooth activation function like the ReLU or hinge function, which is essentially the positive part function that you see here. Also in this machine learning, non-smoothness may play a role. So this is, therefore, there's a whole zoo of non-smooth optimization problems that we want to solve. And the question is, how can we solve them? And one idea is to use optimality conditions, and this motivates also the title of my talk and the focus of my talk. So to motivate everything, I start with the smooth case. So here I have again the constraint optimization problem. So we want to minimize our function f, such that these a set of equality constraints and a set of inequality constraints is fulfilled. So if we want to solve this problem, there are some constraint qualifications, which I will introduce in a minute. So they are, for example, properties of the Jacobian of the constraints. And based on these constraint qualifications allow then the formulation of optimality conditions, such that an optimizer has to fulfill these optimality conditions. So this is a necessary optimality condition or sufficient optimality condition. So if you have a point that fulfills this sufficient optimality conditions, then you know that you are at an optimizer of this problem. And why are these optimality conditions interesting? Because they build the basic blocks for the basic building blocks for numerical algorithms. So almost all numerical algorithms try to find points that fulfill these optimality conditions. And therefore, if you have these optimality conditions, you can then design numerical algorithms to compute the solution of your unconstrained optimization problem. So this is the setting in the smooth case. I will now go into a little bit more detail about these constraint qualifications because we will see parallels for the non-smooth case. So first the optimality conditions. So here are first order necessary condition, first order because we have here only first order derivatives, and necessary because an optimal point has to fulfill these conditions. So if we have such a local solution of our constraint optimization problem, and we have in addition that the target function and the constraints function are C1, so continuously differentiable, and the constraint qualification holds, then there is a Lagrange multiplier lambda such that these conditions are fulfilled. So if you ignore the inequalities for a moment, then this is just a system of nonlinear equations, and therefore you can apply your favorite solver for a system of nonlinear equations to find a point that fulfills these optimality conditions. The important point here, or the important points, are the constraint qualifications, and this is what I will introduce in a minute. So given that this constraint qualification holds, such Lagrange multipliers exist, and depending on the constraint qualification, there might be a unique Lagrange multiplier or there might be several Lagrange multipliers. So this depends on the constraint qualification that you choose. So one prominent constraint qualification is the so-called LICQ, so linear independence constraint qualification. And for our general constraint setting, so where we have the equality constraints and the inequality constraints, we collect all indices where the constraints are fulfilled with equality. So they form the active set, and we say that the LICQ holds if the Jacobian of the gradients with the indices in the active set are, so if these gradients are linearly independent. So this is the main property here, that I have a set of linearly independent gradients, and this also motivates the name of this constraint qualification. Another constraint qualification is the so-called Mangasarian-Fromowitz constraint qualification, which is a bit more complicated. So we have again the linear independence, but only for the indices of the equality constraints. And then we have further properties for all indices that are active and in the inequality set. So there has to exist a vector W such that this scalar product, I always assume that gradients are lying vectors, therefore I have no transposed here, so this is just a scalar product, that this is greater than 0 and should be equal to 0 for all equality constraints. So this is a slightly more complicated constraint qualification. So this is the setting for the smooth case, and one can say that this MFCQ is weaker than LICQ, such that when LICQ is fulfilled, one can show that MFCQ must hold. So now we turn to the non-smooth case. So there things get a little bit more complicated, because if I assume that f is now only locally Lipschitz continuous, but not differentiable everywhere, then I have to look at more general derivative concepts to derive optimality conditions. So for example, if you look at the directional derivatives, which are available in this setting, so I just state the definition of the directional derivatives. Here it is important that this t is always larger than 0, such that I have a positive scaling here. And then we have the necessary optimality condition that this directional derivatives has to be greater or equal to 0 for all possible direction d, if I'm in the unconstrained case. The next one are the so-called Clark generalized gradients. So they form a set of subgradients. So this is this Clark subdifferential, which is, well, has a slightly complicated definition. So due to this locally Lipschitz continuity of f, I know that f is differentiable almost everywhere. Therefore, I can take such a sequence that converges to x, so such a sequence exists due to the fact that f is almost everywhere differentiable, such that the gradient exists. And then I collect all the limits of the gradients. So they form the so-called limiting gradients. And if I take the convex hull, I get the Clark subdifferential. And again, I can derive a necessary optimality condition for this Clark subdifferential, namely that 0 must be an element of this Clark subdifferential. Furthermore, you can generalize these so that you can also look at other derivative concepts, for example, the Mordkovich subgradient, which is defined for the finite dimensional case. So in my whole talk, I will concentrate on the finite dimensional case in this book of Rockefeller and Betts. So Mordkovich introduces this in the infinite dimensional setting. So in his book, he looks at the infinite dimensional setting. Here I concentrate myself only on the finite dimensional setting, and therefore I cite Rockefeller-Betts here at this point. So as you see, this definition is even more complicated. You have a regular subgradient here. So I don't go into details, just to illustrate to you that there's a whole zoo of derivatives in the non-smooth case. And again, we have for this Mordkovich subgradient a necessary optimality condition, namely that 0 has to be contained in this set again. So there are already quite a few optimality conditions for the non-smooth case. So the question is, why is it necessary that we propose another one? So the point is that you have to, for your numerical algorithms, you have to check these optimality conditions or design an algorithm based on these optimality conditions. So here you have to check this inequality for all these, which is just a nightmare to actually verify that this inequality is valid. If you look at this Clark subdifferential or Clark subgradient, one can show that if you look at the absolute value evaluated at 0, or minus the absolute value evaluated at 0, that these two sets coincide. So the Clark, or this necessary optimality condition, does not distinguish between the case if you have a minimum, so if you are at the kink in the minimum, or if you are at the maximum. So this is more or less the same as in smooth optimization, where you have the condition that the gradient has to be equal to 0. So this is somehow related here, that you cannot distinguish between a minimizer and a maximizer. Okay, so and these observations, so there are quite a few optimality conditions, and they are not that easy to fulfill or are not that constructive, motivated us to derive further optimality conditions. And now we turn to our class that we want to look at. So these general derivative concepts have the advantage that you can look at every locally Lipschitz continuous function, and you can apply these optimality conditions. So if you want to generate a more constructive optimality condition that can be used in numerical algorithms, we decided to restrict ourselves to a class of functions such that we can derive an optimality condition that can be used in a numerical algorithm. And for this purpose, I introduce first the so-called piecewise smooth functions and piecewise linear functions. So Stefan Scholtes in his habilitation studied this function class quite a lot, and he actually studied piecewise differential equations. And therefore, I keep the M here. In our setting, so for the optimization, M is always equal to 1, but you can use the definition that I will give here also for non-smooth equations. So what is the setting? So we have here a subset of the Rn, and we have a finite set of functions. This is important that we have a finite set, Fi. And then our function f that we want to look at is called a continuous selection if the function value of f at x is contained in this set. And this has to be true for all x in the set U. So then we have a continuous selection, which means that we always assume that our function is continuous. So this is important because in the literature, there are different assumptions on whether the function is actually continuous or not. But here in our setting, we always assume that our function is continuous but not smooth. So then we have the so-called PCR functions with an R that is either a natural number or infinity. And these PCR functions are continuous selections. So we have again that the function value is an element of a finite set. But in addition, I require that there is a neighborhood such that the functions, so these selection functions, are CR functions, so R times continuously differentiable in the neighborhood of the point where I evaluate the function. And so therefore, this is PCR for piecewise continuous with piecewise smooth derivatives up to order R. So since this is a quite complicated name, these PCR functions are also called piecewise smooth. And this is the point that motivates the definition here. And if all selection functions are piecewise linear, then f is also called piecewise linear, which is a special case of this piecewise smoothness. So this is an upper set of our functions that we want to look at, because now first examples, piecewise linear and piecewise smooth examples. So Nestorov proposed a variant of the Rosenbrock function. So the original Rosenbrock function is a very prominent test problem for smooth optimization. This is the banana shape valley with one optimizer, and Nestorov proposed this non-smooth function. So as you see, here are only absolute values, no nonlinearities, and therefore this is a piecewise linear function, as you also see here in the picture. The minimum is somewhere here at the point 1, 1. And you can scale this function. And the interesting point is that this function has probably, which is shown in this paper, 2 to the power of n minus 1 Clark stationary points, which means that 0 is contained in the Clark subdifferential. However, only one of these n to the power n minus 1 points is actually a minimizer, which is the 0.11 in the two-dimensional case. And therefore, optimization algorithms tend to be stuck in these Clark stationary points before reaching the actual minimizer. So this is one point that is also important to keep into account, that we want to distinguish such Clark stationary points from actual minimizers. Then a piecewise smooth function. This is the so-called half-pipe function. You will see in a minute why we call it half-pipe function. So here we have again the max function, and this nonlinear term here. If you look at this for some time, you get this representation of the function. So we have a quadratic part here. We have also a quadratic part here and a constant part. And if you look at the picture of this function, you see here the half pipe. So this is the quadratic part. Then we have here actually a linear part that connects the quadratic part to a constant part here. And therefore, this is a piecewise smooth function because we have the selection functions, finitely many. And this is also, so both examples are actually non-convex, making the optimization more interesting. So now I come to our class of functions that we want to look at and for which we derive the optimality conditions. So this is called CDFs functions, because we have for any d in the natural numbers, so this could be also in infinity, the set of functions f that map Rn to R and that have such an abnormal form, where we have here one function capital F that maps to the Rs. So Z is an S-dimensional vector, and Z is defined by the value of F at X, Z, and absolute value of Z. So this defines the so-called, so the values of Zj or Zi. And then the target value, so the value of the function F, is evaluated by this phi that only gets X and Z as values, as arguments. And this so-called abnormal form concentrates the non-smoothness just in this absolute value evaluation. And this allows us to exploit quite some structure. And you will see this when we come to the actual optimality conditions. So as I said, the non-smoothness is located in this absolute value evaluation, and therefore the components Zi of our vector Z, they are called switching variables, because if they are 0, you are exactly at the kink of the absolute value, and then the function is non-smooth. And therefore they are called switching variables, because then you switch from one side of the absolute value to the other. Okay. Yeah, switching variables. So one example again. So again, the half-pipe function. So we have here the representation in the max evaluation. So max and the absolute value are actually equivalent. Therefore, I show you here the reformulation of the function in the max term. So here only using absolute values. And now we want to formulate this in this setting. So you can see this also as an equality constraints or S-equality constraints and corresponding function evaluation. So for our half-pipe function, we can formulate the Z's as shown here. So x1 is an argument of the absolute value. Therefore, this becomes our first switching variable. Then I have here another absolute value. Therefore, this becomes the argument, or this becomes Z2 as the argument of the next absolute value. So these three equalities then define our function capital F with the arguments X, z and the absolute value of z. Then the value of the target function just depends on x and z using these two components of the z vector. Okay, so why is it interesting to look at this special kind of functions? Because if we assume that d is greater or equal to 1, which means that in this definition, f and phi are differentiable with respect to their arguments, if you treat this absolute value of z as a variable on its own right, then the following matrices and vectors are well defined. So you can differentiate with respect to x, this is denoted by z. You can differentiate with respect to z, this is denoted by m. And due to our assumption that I forgot to mention that at each zi, it was stated on the slide, at each zi depends only on the zij's defined before. This is a strictly lower triangular matrix. And the same is true for L, where we differentiate with respect to these absolute value. And finally, we have the gradients of the target function. Okay. Furthermore, we define for our switching variables the signature vector, just storing the signs. And if you use this diagonal matrix, then we have the diagonal matrix given by the signature vector. So this is all the information that I can get due to this assumption that I have this abnormal form, that I have a function that admits an abnormal form. Furthermore, as I said before, only if I'm at the kink, then there's a non-smoothness, and therefore I collect all the so-called active kinks where the sign is equal to 0 in this index set alpha, which defines the active switching set, because there actually a non-smoothness occurs. Okay, again the half-pipe function to illustrate the concept, as I showed you before, the reformulation using just the absolute value. And then we have here our representation with our equality constraints defining our capital F and the target function that defines our small f. So if I differentiate this with respect to x, then I get the 1/2 here and the 2x2 here, everything else is 0. There's no z on the right-hand side, therefore our matrix M is equal to 0, and an absolute value occurs here, and therefore I have these two non-zero entries in our matrix L. And since my other main research topic is algorithmic differentiation, I couldn't resist in putting here the reference to algorithmic differentiation, because the matrices that I need, so the structural information for our function abnormal form, can be provided using an extended version of algorithmic differentiation, for example, using our AD tool ADLC. So now I prepared the ground to formulate Kink qualifications. So as I said, the non-smoothness occurs only at the kinks where the absolute value is equal to 0. And in relation to the constraint qualification, we define here the Kink qualifications. So we say that at a point x, the LIKQ, so the linear independent Kink qualification, is fulfilled if for the corresponding signature vector, so that collects the signs of the switching variables, and the corresponding index set alpha, which collects all the absolute values that are evaluated at 0. So then you take the gradients of the z's, which are well defined in this setting due to our assumption on the smoothness of our capital F. So and this builds a Jacobian matrix with this dimension, and we assume that this Jacobian matrix has full row rank. And this is really a nice connection to the LICQ, because there we also had the the linear independence of the Jacobian of the constraints. Another Kink qualification is the Mangasano-Formowitz Kink qualification as a generalization of the MFCQ. This is a little bit more complicated because you have here, you want to examine one point X circle, then you look at all the signature vectors that fulfill this relation. So the formal definition is given here. What is meant is that if sigma circle is not equal to 0, then this has to have the same sign. If this is equal to 0, sigma can have either sign. So then you can, using this partial ordering, you can define a Jacobian for all signature vectors that fulfill this partial ordering. And MFKQ is fulfilled if there exists a vector V such that this product is component-wise greater than 0, or if this equation has only the trivial solution. So as I said, this is strongly related to the constraint qualification MFCQ and similar weaker than LIKQ. So now if you think back on the smooth case, so we had the constraint qualifications and then the optimality conditions. Here we have the Kink qualifications and then the optimality conditions. Sorry, I forgot the examples. So there's our Rosenbrock function. So here you see the argument space for n equal 2 in the two-dimensional case. Here you see the area for the different signature vectors, and the two stationary points in this for n equal to 2 are marked by the green circles, and this is the actual minimizer. If you look at these, so the blue lines are always the non-differentiable areas, and if you examine this closely, one can show that LIKQ holds for this example, and since this is stronger than MFKQ, then also MFKQ holds. If you look at the half-pipe function, so again, a two-dimensional argument space, therefore you can illustrate this quite nicely. And you see here the areas with a signature vector that does not contain any 0. And on the non-smooth blue parts, you see that the signature vector always has one component equal to 0. And due to this fact that this non-smoothness goes into this one in a tangential fashion, here at that point LICQ is not fulfilled, and also you can also verify that MFKQ does not hold. So we have two examples. Here both Kink qualifications hold. Here neither holds. Therefore the question is there an example where one holds and not the other? And for this we looked at this inverted lemon squeezer. And if you look at this lemon squeezer in detail, one can show that LIKQ does not hold, but MFKQ holds, such that we really have an example where the weaker Kink qualification holds, but not the stronger one. So now the optimality conditions. So necessary minimality conditions based on the Kink qualification, namely LIKQ. So I assume that the LIKQ holds, so the Kink qualification with a signature matrix sigma circle. And then just to keep these formulas short, I introduce further matrices, but this is really to shorten the notation here. So if LIKQ holds, then X circle is a local minimizer only if there exists a Lagrange multiplier. And here we see the connection to the optimality condition in the smooth case if we have the two following conditions. So the first one is this. This is called tangential stationarity. And we have here the Lagrange multiplier multiplied with the Jacobian, which Lagrange multiplier, so this vector has to lay in the range of this matrix. And on the other hand, we have this normal growth condition for all indices in the active switching set. So the proof is given in this paper that is cited here. So looks at LICQ, and therefore you see again the strong relation to the smooth optimality and KKT conditions for this branch problems. So if we look at different signatures here, they define the branch problems. So, and this is one advantage to locating the non-smoothness in this absolute value. because then you can use the whole machinery of smooth optimization for the branch problems that are defined by different signature vectors. And an important point, in contrast to the optimality conditions that I showed you at the beginning, so directional derivatives, Clark subdifferential, Modokovich subdifferential, LIKQ, so the full rank of our Jacobian matrix, as well as these optimality conditions, they can be checked in polynomial time. So you really can use in your optimization algorithm a polynomial time approach to check whether you are an optimal point, whether you are at an optimal point, and if not, then these optimality conditions will provide a descent direction. And therefore, as I showed you in the smooth case where we have constraint qualification, optimality condition, numerical algorithm, you have here exactly the same setting, a Kink qualification, optimality condition, and now we can use these properties or these equalities and inequalities to build an optimization algorithm on this, because this also provides a descent direction. So some further remarks. So it's also possible to derive sufficient optimality condition under additional assumptions. And if you look at the stationary concepts that I showed you at the beginning, we have that tangential stationarity and normal growth. They imply Modokovich stationarity, which implies again Clark stationarity, and Clark stationarity implies tangential stationarity. So we have here a really nice relation also to the already established stationarity concepts, optimality conditions in the non-smooth case. Further remarks. So as I said, we have the Kink qualification, optimality condition. So there's also the possibility to formulate optimality conditions without Kink qualifications. However, then you lose the possibility to test it in polynomial time. So at least we conjecture so far that it's not possible to test these optimality conditions that we derive without Kink qualifications in polynomial time. MFKQ so far was not helpful for optimality conditions, but for subdifferential regularity. So if we have MFKQ, then one can show that our function is subdifferential regular, just as a side remark. And as I already remarked, we can build now algorithms based on our optimality conditions, because you can constructively compute descent directions if these optimality conditions are not fulfilled. And finally, so far I just presented results for the unconstrained case. It's also possible to extend our Kink qualification concept for constraint non-smooth optimization. And this is done in this paper by Hegerhorst, Schulchen, and Steinbach. And this appeared last year. And this makes also the connection to the next section of my presentation, namely the relation to MPECs. So as I said, it's possible to extend our Kink qualification for constraint non-smooth optimization. And for this, we define an abnormal NLP. So an abnormal NLP is an optimization problem of the form I minimize F, I have equality constraints, inequality constraints, and all these functions are CDFs functions component-wise. So this is a quite straightforward generalization of the unconstrained case. Then I have to define the MPEC. So an MPEC is a general MPEC is a minimization problem of this form. So I have a target function. I skip the dimensions here because it's just to give you the overall picture. I have this target function, I have equality constraints, inequality constraints, and in addition, sign conditions on these variables u and v, as well as a complementarity condition. And an optimization problem of this form is then called mathematical problem with equilibrium constraints. These MPECs arise in many applications, in economy, multi-level games, chemical engineering, and there's a whole bunch of applications where you can use this MPEC idea to describe your application. And now the interesting point is, so as I promised, the relations of abnormal NLPs and MPECs, that the problem class of abnormal NLPs is actually equivalent to this general MPECs. And this was the subject of a PhD thesis by Lisa Hegerhaus-Schulchen at the University of Hanover. And furthermore, coming back to our Kink qualifications, so the LIKQ for our abnormal NLP holds at a point if and only if the standard constraint qualification for the MPEC holds. So there's a really nice relation between our abnormal NLPs and general MPECs. First on the problem class itself, but also on the constraint or Kink qualification. The situation is a little bit more complicated in the MFKQ case, because here we have in the MPEC case the MFCQ, so the Mangasarian-Fromowitz constraint qualification, and this implies the MFKQ for the corresponding abnormal form. However, the other direction is not fulfilled. So here we have not this nice equivalence relation. And the proofs for these two lemmas can be found in this paper by Hegerhaus-Schulchen and co-authors, which appeared this year in Optimization Methods in Software. So this brings me to my final slide, summary and outlook. So I started with the general concept of optimality conditions for non-smooth problems. I then concentrated myself on abnormal target functions. So these are the CDAbs functions that allow to the formulation in an abnormal form. We can compute the derivatives that are required for all these constraint Kink qualifications and optimality conditions by algorithmic differentiation, which means as soon as you have a source code to evaluate target function, then you get this abnormal form for free if you apply an appropriate AD tool. This allows you to verify the Kink qualifications, at least for the LIKQ in polynomial time. For this LIKQ, we have optimality conditions that can be tested in polynomial time and allow you also to compute the descent direction. And we have also optimality conditions in a broader sense without Kink qualifications, but then they are harder to verify. And there's always a lot to do. So we conjecture so far that verifying this more general Kink qualification is NP hard. So far we were not able to prove it, but we assume that this is true. We want to exploit the relation to the MPECs in more detail. And naturally, as I said, we have the setting Kink qualification optimality condition solvers. We want now to establish non-smooth solvers based on our optimality conditions. Thank you very much for your attention.
Fantastic talk. Thank you very much, Andrea. What an excellent talk. Wonderful. So first of all, I'd like to open the questions up to the audience. So if you have any questions, please post them in the Q&A section of Zoom, and I will be reading them out as soon as they come in. While we're waiting for those questions, Andrea, I have a couple of questions for you, if you don't mind answering them. So have you thought about other constraint qualifications and whether what you're proposing extends to those?
So we have looked at it. So for example, Guyon constraint qualification. So there are several other constraint qualifications, whether they can be extended. But since we really like the idea about this test in polynomial time, and this is only possible as far as we see it for this LIKQ, we concentrated somehow on this LIKQ, because already the verification of this MFKQ seems to be quite hard. And if you look at other constraint qualifications, they are even more general, so it's probably even harder to verify them.
I agree, yeah. Yeah, because they are more general, right?
Yeah, exactly. So we have looked at them, but as I said, it's probably even more difficult to check them.
Okay, so let me read a question from Christoph Helmberg. Great talk, thank you. For what kind of convex sets is the support function an abnormal target function?
I must admit that I do not completely understand the question. So the support function of a convex set, do you mean that this is so the function that is 1 at this convex set and 0 otherwise, or something like that?
Yeah, so I think it's where it's non-zero.
Yeah, that is, so the indicator, that was what I was looking for, so the indicator function. The problem with an indicator function is that it's not continuous. So we are always thinking about an extension for non-smooth, not continuous function, but so far we restricted ourselves to the continuous setting. Okay. Well, this would, so the question is how you define the C then. So the optimization problem would be you maximize the scalar product of a vector C times X, and you want to describe the vector X as contained in a convex set. So this would mean that we have an optimization problem of this form, that you want to maximize this. So minimizing, maximizing is the same. So this is just multiplying by -1. And you have to describe this X in C, so this feasibility by, for example, probably an inequality set. So the question is whether you can describe your convex set as such an inequality constraints where the component functions are abnormal. Yeah. Okay. Now I understand the question. So you have this min-max. So min-max is okay. So min-max is an abnormal form. You can reformulate this. Sorry for this. Took a while until I understand the question. So you have a minimization of a max of something. So this min-max coupling is an abnormal, can be described in an abnormal form. This is not a problem. So this fits nicely to this setting. So the F is then the max of something. So which means that this is an a CD abs function. Then the only point is whether your feasible set, so the X in C, can be described as such an inequality that also fulfills this restriction.
Okay, fantastic. Thanks. Wonderful. And I have another question for Andrea. So you mentioned before that one of the reasons why we want to look at these optimality conditions is because it inspires to develop algorithms for optimizing solving these optimization problems. Can you talk a little bit about some of the algorithms that you envision using these optimality conditions, and what are the challenges that are being posed because of these optimality conditions?
Okay, so I just put a few acronyms here. So this is our active signature method. This is actually for the minimization of piecewise linear functions. And we are actually quite happy with this algorithm because in the piecewise linear case, you can always check these optimality conditions, and then there are even sufficient optimality condition. So this is quite okay. The challenging point is this one here, SIAM. So this is the successive abs linear minorization. And here we look at piecewise smooth functions. And using the technique of abs linearization, it's possible if you have a piecewise smooth function, using, for example, the extended AD version to generate a piecewise linear model. So this would mean that we use, for example, the active signature method for this piecewise linear model, and then have this as an inner loop, like an SQP method, where you solve quadratic subproblems. Here we solve piecewise linear subproblems, and then we have to couple it back with the SIAM approach. So the theory of these optimization algorithms, this is fully developed. So therefore, there are already several papers. Currently, we are working on an efficient implementation. So we have some MATLAB C implementation, but we really want to cover and cover, so the main point is here more stability of the implementation robustness. So it works for the standard test cases. There we are quite okay. But to really make it stable, there's still some work to do.
And are these codes, some of them, even the rudimentary versions, are they available?
So far, they are available on request. So if you send me an email, we can certainly provide them. But as I said, we are still working on the robustness, and therefore we do not share them because, well, then people try them and it's always difficult. And therefore, yeah, at the moment, we're a bit restrictive giving them out of the hands.
Okay, fantastic. Well, if there are no other questions for Andrea, normally if we were in a live audience, we would give you a very nice round of applause for a wonderful, excellent talk. I really enjoyed it very much. And I hope this brought up some very interesting thoughts in our audience. We have one more question. Salmon can be extended with another kind of paradigm like branch and bound. Is that a possibility, do you think, Andrea?
So yeah, this would be one. So as I said, this is this active signature method is one approach to solve this piecewise linear problems. It's always possible to formulate this piecewise linear problems as mixed integer problems. So therefore, you could substitute this in a solver with an branch and bound, so a mixed integer solver. So this would be an alternative, sure.
Okay, great. So that question came from Angel Rojas. So thank you for that question. Okay, so if we don't have any other questions, thanks again to our speaker for a wonderful talk. And for our general audience, I hope you enjoy the rest of the day and the rest of the conference. Thank you for attending.
Thank you very much for your attention.
Bye-bye.
Bye.